A little bit more motivation, but this is a technique I'm going to ask you to employ. I'm going to give you a problem in the upcoming future, and I'm going to have you compare a Bootstrap answer to a Bayesian answer to an asymptotic answer, so that you can compare these different lines of thinking of what different ranges of statisticians are doing. So I will ask you to do this, and I tend to think with things like this that are very computational, you only understand what you actually do. So in code about understand the details. Luckily, bootstrapping is really easy to implement. It's like 2 lines of code in Spirit. Okay, so just as a motivator for the Bootstrap, consider some data set. It comes from some distribution. It's important that everything is IID. We're going to be sampling with replacement from everything, and the only way we can really justify that is sampling from replacement is a sample from the original sample, so long as everything is IID. We can shuffle everything in a hat and just select things. And those are actual samples. There are versions of the Bootstrap, block bootstraps, where you block things together that have dependent structure, and they're pretty close to doing the right sort of dependent stuff, but you would need to know which blocks of data are dependent. So if you have correlated data that was very block dependent, you need to sample that as a block. So there's lots of incarnations of the Bootstrap. There's a parametric version, but what I'm going to start out with is the non-parametric version. And so this is basically what you would do if you didn't know anything about this, and you didn't want to impose it, you didn't want to model it, you didn't want to know anything about, you didn't want to actually say what f was and build any mathematical assumptions in, you just wanted to use the sample itself to do everything. And that's where the Bootstrap gets its name. You're picking yourself up by your bootstraps, you don't know what to do, you don't want to do any modeling, but you got to do something. It's going to be brute force. So the name is semi-satisfying, but I guess it could apply to anything. Also, if I didn't know what to do, I got to do something. Something's not very definitive. Anyway, we'll take something to be the Bootstrap in this case. So not a great naming device, but I kind of like it too. So it sticks with it. So you want to understand some test statistic. So I just call that a stat. You could call this a transformation of the data if you wanted to. It's some function of the data. It's all of those things. So those are all synonyms for you. And I wanted to understand the behavior of this, but I recognize by going out and collecting these are random values. And a function of random values is also a random value. So technically those are random variables and those have a definition. Just real quickly, does anybody know what the formal definition of a random variable is? Kind of fun. I used to start with this, but I don't know if it's overly important.
It's a function from your probability space to the real numbers.
Could be the real numbers, right? Doesn't have to be the real numbers necessarily. It really means that you can invert back. If I have this test function and I know what this test function is, this is some value, I can map back to the x's that form it, and I can build a probability distribution on those x's. So it means there's an inverse map that I can infer to the actual elements that form that test statistic. So just like in rolling some dice, we could go over this and review. If I'm rolling 2 dice and I want to know the ways that they add up to 7, maybe that's my test stat, is the sum of the faces of the dice. There's lots of ways I can formulate the coming up with a 2 dice roll and having them add up to 7. I could get a 6 and a 1, a 5 and a 2, a 2 and a 5, a 3 and a 4, a 4 and a 3, so on and so forth. And I could come up with the probability measures on those faces. So I know what the probability measure on each one of the faces is. Presumably it's 1/6 if it's a fair die. And I could enumerate the probability of getting a 7 by enumerating the different ways we could form a 7 and add all those probabilities together. So if I can invert back to the original element space, that means it's a random variable. It means the inverse mapping exists. If you don't like that, it's just a random function. You know, you can think about that. But I gotta be able to assign the probabilities to it. So, okay. We're not going to get super technical. I'm not going to grade you on measure theory, but I like to sprinkle that stuff in. Just make sure some of you that know what this stuff is, feel comfortable that I need the more technical definition. I'm going to usually omit it, but maybe we'll talk about it for 2 minutes. If you want to know more about that, there are measure theory classes that will drive you crazy with things, and you'll go, I know exactly how to do this, but I have to understand the generalization of it all. Okay. We want to understand some test stat right here that's random itself, and we want to try to understand it not just by some numerical point estimator, but we want to understand how uncertain it is in the first place. And so what the Bootstrap does is it mimics what you might want to do, but it does it in a for loop. I'm going to call cap B right here the number of Bootstrap replicates. I'll fill this in a second. There's 2 steps that I'm going to enumerate here for doing bootstrapping. But the number of Bootstrap replicates, in some sense, and I'm going to change my mind about this, but at least maybe for our first kickoff, we can think about this as the number of times we want to pretend we're running back out into the population and collecting a new random sample. So what I mean is I go back out and I collect a new one of these from the population, and they're going to have new values in there. I don't want to do that because it's too much work. So instead of doing that, I'm going to not go back out into the population and resample, but instead I'm going to resample from this vector. So, and I'm going to do it n times so that the sample size is exactly the same. And the idea is if this is enough data to approximate the underlying distribution f, and if it's not, there's very little you can do. You've already heard before, if you don't have a representative sample, how are you going to do inference on it? You would need to know how you bias the sample. You would need to stratify correctly, and people do this all the time. So I'll point out, when we were going through COVID wave 1, people were trying to figure out, after a while, what the infection rate was. So we kind of knew that there were a lot of positive tests out there, but there were also a lot of people that had didn't have symptoms. And so that mattered. There was this missing sort of latent thing we couldn't see. And so it was important to go out and sample everybody and see if they had the antibodies. They did this in the Bay Area, I think, first. And it's not that surprising. So Stanford ran out, some team of scientists ran around the Bay Area, sampled a whole bunch of pockets, tested them and said, oh, you had COVID in the past. And they ended up telling us numbers like, it looks like at least 40% of the population is non-symptomatic. It turns out it was more like 80 or at least mild symptoms, something like that. And it was important to understand that so that we could evaluate what the true death rate was. Otherwise, we think it's overinflated if we don't account for all the people that have had the disease and didn't do anything to them. They knew that their sampling was a little bit not representative because of the way they did it. And they were able to extrapolate based off of, here's the sample we have, here's what the real population is. There's different genetic groups out there that have different propensities for getting the disease. And they tried to account for that and do an extrapolation out. I know they say don't do extrapolation, but I would say everything we do in statistics is some extrapolation, so it's more like the type of extrapolation you do. I would say interpolation is really extrapolation, where you're extrapolating between points. But if you don't like that, you can call it interpolation. Say that's the good type, and when I try to forecast outside of the bounds of the points, that's extrapolation, but we do that all the time in time series when we forecast. So kind of everything is an extrapolation. So you can try to make up for biases if you knew a lot of things about the population. Okay, so anyway, that's going a little bit deep. We're just going to assume that we have some representative sample. If that's not representative of the underlying distribution, there's very little we can do to figure out what our true inferences, our real inferences should be without knowing a lot of extra stuff. And sometimes in science and engineering, we do know extra stuff. We're going to assume we don't know anything extra for this problem. We don't even know much about f itself. We just know there's some underlying random process. So instead of going back out into the population, resampling over and over again because it's inefficient, it takes time, we don't want to understand the asymptotics based off of n data sets. If I have replicates of n data sets, I would have the number of replicates times n would be the asymptotics, and I'd rather use the data that way. But in bootstrapping, we can kind of replicate that by not going out into the population, but going back to our underlying sample and resampling from it. And the key insight is that a sample from a sample, a uniform sample from a sample, is a sample. So a uniform sample means I'm just sampling each one of those x's with probability 1 over n. And there could be replicates in there, and those replicates would represent, the height of that density function, that it's overrepresented, it's higher than some other values. So a sample from a sample is a sample if the original sample is a representative sample. So that's the idea, that's bootstrapping in itself. And so here's the idea. I'm going to grab these auxiliary data sets, I'm going to call them XB. And XB is going to come from a sample from our original data set X. It's going to be sampling with replacement. I'll just write it down. With replacement. N times. So that my auxiliary data sets have the same asymptotic behavior as our original data set. And I sample with replacement from XR itself. So this is the original data set. And there's lots of ways we can do that. So chances are, if n is big, we sample with replacement from X. If we do it twice, we're going to come up with 2 distinct bootstrap replicates. So I'm going to call these the bootstrap replicates. So instead of a replicate from the population, it's this new type of replicate. And if n is big, bless you, then this is very similar to going back out into the population and resampling. Keep in mind, if we didn't observe something in the original sample, you're never going to be able to observe that in the resample. So there are limitations to it. You might think things like, well, what if I gave this a little jitter? You're assuming some stuff when you do that, and you're assuming everything is smooth around those data points. And that could be a great thing to do, or it might not be a great thing to do, and it depends on the case. That's why there's so many papers that are written. Some ideas apply to certain analyses, and some ideas don't. And then all we're going to do is create a new test statistic. And I'm going to do this by taking my original function t, whatever this thing is. Here's an example, just x bar. Maybe I don't want to learn about x bar, and I don't know any math. And I'm just going to build up this thing from my bootstrap replicates. And that's the bootstrap, is I'm just going to collect a lot of these. And at the end of the day, what I'm going to get out of this algorithm is I'm going to get a sequence of bootstrap replicated test statistics, or transforms, if you want to think about it that way. And what I can do with these is I can draw a histogram of them. And then maybe I do inference based off of this histogram. So just like we were thinking about in our original simulation study. So this is called a bootstrap distribution. Now I want to point out that if we didn't sample things in the tail in this distribution, we're not going to be able to learn those tail behaviors in our bootstrap distribution, so we're going to be missing stuff because it's relatively unlikely to sample it in the first place. Of course, as n gets bigger and bigger, we usually go into the tails and we explore the distribution a little bit more. But the Bootstrap's not going to be able to tell you things that your original sample can't. So, and this is the idea, is I'm going to get some Bootstrap distribution. I can compute the mean of that distribution and understand what the mean of the Bootstrap distribution is. And now what I can do is start to understand uncertainty about that statistic, and I can start to build intervals. So what's the idea of the interval? I want to come up with an interval that comprises the massey part of that distribution. So all this stuff that you've already done in statistics. So question is how limited is this idea? How well does it work? And it works surprisingly well in a lot of cases, probably a little bit better than you might think that it does. I didn't like this because it kind of obviated all the math from trying to understand, transformations, doing transforms, understanding what the real f is, so it made life a little bit too easy. And I didn't like it for that reason, but now I kind of like it. So sometimes when people ask me, what should I do, and I don't want to hire you, because I'm going to create some boutique model for them, some boutique computation, it's going to be really nice and tailored to them. That's what I do for a living, and teach classes, and other things. But if they want to do it themselves, I might say, well, try Bootstrap. If everything's IID, this will give you an approximate answer.
So is the number of samples in the replicate the same as the number of samples in the original X, like the N?
Yes, that's what this is right there. N times. So this is a new data set of N points.
And so the only reason it's potentially a unique data set is because you might be repeating different
That's right.
samples from the original pattern.
That's right. If you had just one data point in this right here, all you'd be doing is reconcocting that same sample, and it's hypercorrelated with itself. So it's really that covariance, which is part of the approximation. If n is big, that covariance is small, and we don't have that dependence in there. So there's a little bit of dependence between these samples, depending on how big n is. Okay, one thing I want to point out is there's two types of asymptotics in this. There's n and there's cap d. Before I erase this, I'm just going to point out homework is due next Friday. That's in a week. That's how I use next. Today is this Friday. And this Thursday is the upcoming Thursday. So that's how I use next and this, just to point out. There's a few hard problems in there. There's a couple of them. Some of them are relatively easy, but I'm just trying to warm you up and understand where your probability theory is. So none of those questions are exactly inference. It's just overlapping what you might have learned last semester or some semesters ago. So give those a whirl. I will point out there are a couple problems, and I'm happy to answer questions during review session or offline and give you hints, things like that. I do have a question about this, real quickly. Question. How many unique Bootstrap replicates are there? Let me be specific. If there's two values in this original data set that are the same numbers, but they're represented twice, I'm going to label those, and I'm going to be specific about which one I got. Okay, so I'm going to be specific about the actual entry I got. So when I'm talking about uniqueness, I have to account for which one of those two numbers I got. So let's imagine the number 6 is represented twice. I have two ways to grab that 6, and I'm going to grab those two 6s in unique ways. I'm going to identify which 6 I grabbed. Okay? If that confuses you, think about these as all unique numbers. And so everything is unique. Just put labels on things that are unique and make sure that you label them so you understand the distinction between the one you grab. So what do you think the answer is to this?
Is it n factorial?
N factorial. So that's the number of ways you would permute everything. So if I wanted to think about the number of ways that I permute this, but it would have the exact same number of replicates, exact same number of things in there. So if I shuffle this around and it's IID, I'm getting the same sample, and that's what n factorial would represent. Most people don't know the answer to this. So it has something to do maybe with combinatorics. Any other?
Is it just like n to the n?
N to the n. So n things, how many times? It's not quite. We can think about what that means later. It's not n to the n.
Maybe n to the n divided by n factorial?
Not quite. But we're at least thinking about all things correctly. I'll have to dissect what that would actually represent. I'm not that smart. So to figure out, oh, I know you're exactly what the error is. I have to think about it. Turns out it's this. 2n minus 1 choose n. Let me tell you why, real quickly. I'm just going to show you a picture. I've heard 2 to the n a lot. That was a common number in the past. It's like if I'm having binary things in or out of the sample, how many are in or out, but I'm not accounting for replicates, repeated values when we do that. So let me just draw a picture for you. Let's say I have a sample, I'm just going to say of 3 things. I'm going to call this x1, x2, and x3. That's my original sample. So, just so I can draw a picture for you. And I want to come up with maybe some standard notation that I can use to exemplify the replicates. So I'm just going to give you some examples. Here's just a picture. These are examples. So what I'm going to do is I'm going to come up with a stars and bars sort of argument. Okay? If you've ever seen this sort of thing, but it's all these like grabbing balls from urns sort of arguments. I'm just going to say this picture means this. I'm going to bring in not n bars, but n minus 1 bars to represent the replication process. So this sample right here, x1, 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 this would be unfortunate if you got this in a Bootstrap replicate. But it'll happen, it's part of the variation of the process. Could have happened. I'm going to represent this like this. Star, 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 bar, bar. Okay, I'll tell you what I'm doing in a second. These are partitions, and what I'm representing is this is the partition for x1. This is the partition for x2. There's no balls in that. There's no stars between these bars. Okay, if you don't like my undergrad sort of explanation, too bad, I like this one. So, and there's nothing in here, right here. So all of the samples are to the right of this. How many separators do I need in 3 data points to separate things into these groups? I only need 2 separators because I'm going to include the endpoints to represent things. So let me just come up with another example. So here's an example. I'm going to come up with star, bar, star, bar, star. This is going to represent x1, x2, and x3. There's 1 point in x1, there's 1 point in x2, there's 1 point in x3. Let me do just another one. One more. Star, well, I'll do bar, star, star. My stars are changing definitions, but they're still stars. So what does this represent? X2, x2, and x3. And it didn't matter which order I put these things in because it's IID, so I just picked an order. So the question is how many different partitions can I come up with of the stars? And so what I've got is I've got how many things here? The sample size was 3. How many bars did I need to come up with the separators? 3 minus 1, which is 2. If I add those together, that's the 2n minus 1. In our case, that's 5 here. So, but then I have some uniqueness problems that I want to deal with. So I have 2n minus 1 factorial ways that I can rearrange the stars and bars. But then I have some repeats in here. So how many repeated things in here? I don't care if this was like this or like that. So I have to take out the orders. So I have to take out the orders of everything, all of their label names. How many stars are there? There's n factorial ways that I can permute those. How many bars are there? There's n minus 1 factorial ways that I can shuffle the bars. It doesn't matter how I came up with the bars or the stars. And that's the number. So number of permutations of stars and bars, number of ways I can rearrange the stars and still have the same unique pattern, number of ways I can rearrange the bars. So it's 2n minus 1, choose n, or choose n minus 1 is the exact same thing. So that's the number, and that's how you remember this. So the stars and bars exercise. So I like pictures, and I'm going to start with pictures. If I can explain things with pictures, I'll do that. So if we need formal proofs, we'll do that. Does everybody understand this? Cool. I had somebody like invoke like the Einstein-Rosen-Bridge blah, blah, blah semester where I was like, I don't know if this proof is correct. I have no idea. So I don't know why we had to invoke physics to do this. So sometimes you might overshoot my level of proof. I gave him full credit because I couldn't even tell if that made any sense. I thought it was completely wrong. So anyway, this is the answer. Feel free to ask me questions along the way and I'll see if I can explain them. This number is big.
Is it like bigger than n factorial, smaller? Like where is it kind of sitting as 1 to the n factorial?
Yeah, so I'll let you investigate. So those things cross each other. So point is this number is huge. So really, really big. And that's important. So how big do you think this number of n is 10 is? It's bigger than you think. So it seems like n needs to be extraordinarily large for this to work, but it actually works better than you think because there's so many replicates that you can form out of this. So there's lots of ways to capture the variability in the sample. Okay. Let's do some experiments. Oh, I did mention doing this with x bar. Bootstrapping is a little bit silly, and the reason why is we've got the central limit theorem. We know something about that. Maybe n is equal to 10 doesn't kick in the central limit theorem fast enough, and it has to do with how wiggly that distribution is in the first place. So everything comes back to how wiggly distributions are, how well you do, and that has something to do with the variability of that distribution. So I tend to think everything's about variance and not about bias. I like to focus there. Okay, let's do some sim. I wrote a piece of code. This piece of code is on the website, so you can download it. Play around with it if you like. Let me just explain what some of the pieces are here. Just the master of the lights. Nobody, I guess nobody. No fan? No fan. That's pretty dark, huh? Like it? If anybody doesn't like it, send a complaint to the dean. They love that. Actually, just come and see me. It's the right thing. I'll see if there's any way I can appease their wants. Chances are not always. Everybody can see this? In the back?
Yeah.
Cool. So here's my code. It's like a shadow now, huh? Top of the code just says Bootstrap example. It gives me the Bootstrap stats and how many times things were replicated. So that's all it does. If I wanted to look at those, everything internal here will run by itself. So I wanted to know what the Bootstrap replicates were, how many times I've replicated things, and some statistics about the Bootstrap. I could look at those. Here's my F. So this essentially is my F right here. And let me just show you something. We're going to be diving into this soon. Let me just show you what a mixture model is. An additive mixture model. There's many types of mixture models. So my F looks like, of course. This technically is called a Gaussian finite mixture model. So the finite part has to do with the number of components. In our case, there's 3 normal distributions represented. So there's 3 components, 3 is a finite number. This lets you know there are ways of doing this in infinite manners to get even smoother, refined stuff where you don't know how many mixtures there are up front. I'm going to have you play around with the finite versions, and I'll talk about selecting the component number later. I'll tell you maybe what somebody would do if they were a card-carrying Bayesian or something like that, had a couple of years of grad school under their belt, but we'll try to come up with the ideas that are a little bit simpler, but basically extend to more complicated things. So it looks like this. I'm going to end up just looking over K, goes from 1 to 3. Usually I call that cap K right here. So in our example, cap K is 3. And I'm going to have some weights, weight K, next to some normal distributions, X, and I've got mu K and sigma K. So these might represent some densities right here. So this might be 1 over square root 2 pi, sigma K. I always pull my sigma K outside. Sometimes you'll see that squared and tucked into the square root value. E to the minus 1/2, X minus mu K, the centering parameter, divided by sigma K squared. So those would be the densities right here. These weights right here that we have, WK, are going to sum to 1, and these are all positive. So the probabilities of being in that component. If you wanted to sample from this distribution, there's 2 steps. First, you flip a 3-sided coin for my example with the relative weights. Flipping a 3-sided coin, how would I represent that mathematically? What distribution is that? If I flipped a K-sided coin.
It's like a point mass, like Bernoulli.
It's like a binomial, but it's multinomial. So that's the name. So I'm going to multinomial sample with these weights right here. That's a 3-sided coin flip. If you've ever played Dungeons and Dragons, you're familiar with these sort of things. So you have infinite-sided dice. Okay, is that right? Something like that. Close enough. It's a good approximation. Once I get the component number, the K that comes from that, I'm going to sample from that normal distribution. So I'm going to sample from the normal distribution with the mean and the variance that conforms to that flip of the coin. Okay, so all of the mu's and those weights come together. So all I do right here is we're going to sample. I'm going to come up with a multinomial. This is going to have W1, W2, all the way up to W cap K. There's only going to be 3 values in our example. And I'm going to shoot out from that some K label. I'm going to call it K star. In our example, that's either going to be a 1, 2, or a 3. In this example, it's going to be a 1, 2, all the way up to cap k. And then I'm going to sample the x, I, from the normal distribution. There's the random variable, and there's the mean and the variance. So I'm going to plug those in, and I'm going to sample from that normal distribution. So that's a finite mixture distribution. It gives me multi-modes. I have that coded up right here. I've got my mixture weights. You can verify those at the 1. 1/2 plus 1/3 plus 1/6. And then I'm going to sample from 3 different normal distributions. I've given them all the same variance. Rand_n is just a normal 0, 1 generator. It's the same thing as invoking random normal in parentheses in MATLAB, and there's notation for that in any stat software package like ours. So I have 3 different normals. This is going to be a normal 10-1. This is a normal minus 10-1, and this is a normal 3-1. So if I wanted to scale the variances, I would take the square root of that variance and I'd multiply it by the random thing and rescale that distribution. So that's what I'm going to do. So what I'm going to do, some number of replicated times, this is the number of times I want to run back out into the population. So what I'd like to do in this code is compare what would happen if I ran out into the population to if I bootstrap sampled. So we'll get at least a visual understanding of how close those processes are, how close those distributions are to each other. So I have 3 different normals. So for each replicate, I'm going to do this n times. This has to be the most inefficient way to do it. Probably what you would do is vectorize this, do all your coin flips all at once, and then sample your normals in 3 different blocks. So I've broken this up so that you're sampling every single time individually. I'll usually write the code this way for the class, but I probably wouldn't do this if I were actually doing a real research problem. So what I'm going to do is I'm going to grab a random, and I'm going to check if u is less than the mixture weight. So if it's less than 1/2, that happens with probability 1/2. I'm going to sample for my first component. Or, if that didn't happen, and the mixture weight is between these 2 values right here, 1/2 plus 1/3, then I'm going to sample from the second component. So this would be the next block over, so on and so forth. Otherwise, I'm going to sample from the third component. Does somebody I think you all can understand why this works. There's a name for this type of sampling. Does anybody know what the name is? What I just did? I think I could teach this to a 3rd grader, but I don't know if they would understand what the name of this type of sampler is. So for sampling from a binomial, just 2-sided right here, I have probability P. Let's say that probability is 0.7. So if a uniform is less than 0.7, what's the probability a uniform 0,1 is less than 0.7? It's 0.7. So what's the probability that it wasn't less than 0.7? It's 0.3. It's the other side. This is exactly the same thing. That's known as inverse CDF sampling. So this is inverse CDF sampling, and I'm going to walk you through that in a homework exercise too. I'd like to teach you some sampling principles so that you can invoke them and understand what's happening in all the code, because you're going to be doing the same thing. Anyway, I think this is a straightforward version. I understood this before I understood what inverse CDF sampling is, but it's inverse. Anyway, I generate a uniform and I get a sample from all of this stuff. Then I plot everything. I'm going to just plot a histogram of going back out into the population and understanding what that distribution is. I'm going to plot that for you. Then I'm going to do some bootstrap sampling. And I'm going to be resampling from this same x value. I just want to point out which x value I'm using because I've sampled R of them. I'm only using the last one. So the very last sample I used from the population is the one I'm going to be doing bootstrapping off of. That was just a random choice because that was the last one that I encoded. I didn't want to save them all in this code. So this is the very last sample that we go out into the population and sample with. And I'm going to bootstrap over that, sample and replace. Random sample is a built-in function in MATLAB. And if I invoke the toggle true, I'm saying sample with replacement. So I'm going to do it n times. That's what's right there. You could put weights on the samples. If you don't put weights on the samples, it'll uniformly sample. So each thing with probability 1 over n. So you can reweight that in this function. I'll let you type in help for this, and it'll tell you all the little controls that you have in this built-in function. And then I'm just going to compute my statistic right here. We know a lot about the mean. That's why I want to start with the mean. So we kind of know that that probably should be normally distributed if n is relatively big. How big should n be? They say 30 is good enough, but I can make my underlying distribution wiggly enough that n is equal to 30 won't do it. So then what I'm going to do is I'm going to plot those two different distributions, and we can look at how they compare to each other. So we already plotted the going into the population, that histogram. Here's my Bootstrap distribution. And then what I'm going to do is I'm going to compare those two different distributions to each other. Does everybody know what a QQ plot is? Probably not everybody. So I'm a statistician, about half of you probably know. It's a way of comparing two different distributions. Let me explain what it is next time real quickly with a picture. There's different ways that you can formulate this, but you're plotting the quantiles of distributions next to each other. You can either take empirical quantiles and plot them next to theoretical quantiles, or you can take empirical quantiles from one distribution and plot them against empirical quantiles of another distribution. If the distributions are the same up to location and scale, you will get a straight line. So, and the slope of the line will represent the scale, and the shift of the line will represent how they're shifted. But basically, we'll know that those distributions are the same up to shape and scale. If the tail behavior is different, we'll see that deviation from the straight line. I'll come back and I'll give you a quick 10-minute primer on what QQ plots are. They're my second favorite type of plot. So I love them. They have lots of limitations, but it's something I like looking at. I'd much rather do this than a chi-square test for testing distributions. And I'll tell you why next time. Okay, so let me just run the code. We know what bootstrapping is. We know about what we're doing. I'll just tell you my toggles. N is 500. I'm just doing that so that you can understand the asymptotics in N. If N is big, this should work out pretty well. And then I have some asymptotics in V, how many bootstrap replicates. For my first run through, I'm going to make the number of replicates from the population the same as the number of bootstrap replicates. But there's nothing restricting me from doing that. I could enumerate over every unique bootstrap replicate, and you might ask why we do that, and it's just so that I don't have to order everything and store all of the bootstrap replicates. It's going to be converging to something, and you actually don't need to enumerate all of them to get a really good approximation. So instead of doing that, I'm going to do stats, and I'm just going to throw darts. We'll talk about that point next time as well. We could enumerate everything. And if I crank this number up high enough, you won't be able to tell the difference. So let's run it. Bootstrap. There's my sampling from the original distribution, R times. That's what was flickering on the screen when you saw everything. When I bootstrapped, I did something similar by going back out into the original, the last data set and bootstrap sampling. I just didn't flicker that across the screen, so you never saw that update. I just created the bootstrap distribution. So here's the distribution that I got, and this is kind of fortunate. I like when things work out the first time. It usually doesn't happen. Here's the original distribution. That's the distribution from the population. And you see that label right there. They're a little small. Population, bootstrap. And we notice they're kind of the same. So I'll just point out, that's about 2 point something, and that's my 2 right there. So they're a little bit shifted from each other, but they're kind of in the same place. And if you compare the variances right here, this is like 2.8, and that's like 3 right there. Roughly the same. We do see some deviation going out into the population, gave me a work stream value right here, and I didn't resample that very often, it seems like. But they're kind of close to each other. If I want to compare these two distributions, what I can do, let me just explain it in 1 second, is I can look at the, there's 500 data points, so I can look at the 10th quantile, 10% of the data, see how much data is there, and look at that value right here. I can do the same thing and look at how much 10% of the data is to the left of that, grab that value, and I can plot them next to each other. Then I can merge this thing over, look at 20% of the data, where 20% of the data lives right here, and then plot that value against this value. And I do that for lots of quantiles. I can actually do it for 1/500, that quantile, the 1/500th quantile, the 2/500th quantile. So because the sample sizes are exactly the same, we can actually match those, but they don't have to be exactly the same. So here's the QQ plot for everything. And what we notice is it's relatively straight line. There's a little deviation in the tables. And I would say maybe those distributions are a little bit similar to each other. We see some warble in here, and that tells me where the distributions are deviating. So instead of just saying the distributions are the same or different, I can see where they're different by looking at this plot. I'll point out you can only do this with one-dimensional distributions. That's the huge downfall. So to all of this, is it all has to be 1D because we're just marching down the quantiles in a one-dimensional manner. We'll come back here, I'll explain that better next time. We're gonna play around with this code a little bit and see how this works under various situations. So I might say n is actually just 31. Who's gonna go get 500 samples? I mean, some people do, but we wanna make that small maybe because we only have so much time and money. I might say, let's compare this to some number of large Bootstrap replicates, but I can crank this up because this is something I'm doing on the computer and I can just make that large. I want to point out, n choose, I'm going to just pick this number to be 10. N times 2 minus 1 choose n. Right here, where n is 10, this number is big. That's 92,000. So there's 92,000 Bootstrap replicates. If I just had n was equal to 10, I have n is equal to 31. 31, 31. That number is too big to even represent. So it works better in n than you actually think, and you have control over cap B. Print that thing up as large as possible so that that thing stabilizes. And we'll talk about those asymptotics next time. So that's too big to even represent. That's a number we don't even understand. So you've never seen that number. Maybe, if you're a chemist, maybe. Okay, so do this one more time with these updated values. We'll talk about this for a little while. What I'm going to do next time is I'm going to change the test stat that we're looking at. So this is going out collecting 31 data points from the population, but I've cranked up my Bootstrap replicates. This is my distribution from the population, and this is my Bootstrap distribution. They're kind of the same. My eye is terrible at gauging how close histograms are to each other. They don't look the same. They're kind of the same, but I could end up using a QQ plot to try to describe that. So even though there's a little bit of difference in here, they're roughly the same. Anybody shows me a histogram and says, do you think it's normally distributed? I would say I have no idea. So I can't tell. I can't tell deviance. I can't really tell what's going on with histograms. And histograms are subject to the way we bin them. So I use just the default number of bins in all of this. And you can get some weird visuals out of binning things differently. Anyway, those distributions are relatively the same. And I will say these distributions are relatively normal. I haven't actually checked that. What we can do next time is we can plot the QQ plot against theoretical normal distributions and see both of these are relatively normal.
So is there a point that we could somehow quantify to where doing a certain number of replicates has diminishing returns in terms of the benefit of it?
Here's a good way to do it. Crank it up really high, big number, and see what maybe the mean and the variance of that distribution is, or anything you want to report. And now double that number and see if those numbers are just the same up to however much decimal precision you need. So crank it up, double it again, and see that your returns are falling off. If that number is not, if that number is changing every time I change the number of Bootstrap replicates, keep cranking it up until it converges. So that's my engineering way of saying, yeah, there's a way, and that's how people actually do it. So they're probably not going to invoke any theory to do it. They're just going to do this in a strict Monte Carlo sense and look at the stability of the Monte Carlo estimate. That's bootstrapping in a sense. Later on, we're going to figure out how do we construct these distributions and what are the actual mathematical properties, but we've been able to eliminate all the math just by using this brute force computation. And if you went back to the 60s and showed somebody this, they would be impressed. Nowadays, we're like, computers are pretty good, cool. They do things quickly. So it did do stuff pretty quickly. I was even able to flicker the graph to you and show you what was going on. Let's come back next time and keep talking about this. After we finish Bootstrap, we're going to jump in order stacks, and then the math is going to keep increasing. That's it for now. You guys have a great weekend, and I will see you Monday. I will give you all these minutes back. I promise. So, at some point, if I don't get sick in this class and give you a day off because of that, we'll just take a Friday off. Pay you back in some way that's meaningful. Thanks for your patience.
Is the Slack up and running?
Not yet. Okay. So, I'll set it up Monday, set it up.
Okay.
Great question. Yeah, did I miss it? It's a great conversation happening. It will.
Did I miss the email or something?
Not yet, not yet. I found over the years, I need to wait for that cat to log in.